and or economics before, you might be familiar with marginal cost, marginal revenue, marginal profit, but we are going to be taking a specifically calculus approach to this since it's a calculus class. So we are going to be looking at what happens when basically a company is producing things and selling things. So our first kind of function that we will be seeing is total cost, which is represented by C of X. And so total cost is the cost of producing X products, or X units, I should say, X units of a product. So if your company is producing water bottles, then C of X would be the total cost to the company of producing X water bottles. So the cost function tells us that cost. And you've seen some of these in some of your word problems at the end of these previous homeworks as well. So marginal cost, we can see this little C prime here. So that's our derivative of the cost. So knowing what we know about derivatives, if marginal cost represents in words.
Can you say that one more time?
Mm-hmm. Yes, so the final question is, what does marginal cost represent in words?
Is it profit?
The rate of...
No.
Profit.
Is it the rate of change of total cost at a given time?
Super close. It is the rate of change of total cost with respect to X. So in this case, X is the units we're producing and not time. But yes, it is the rate of change of the cost. So the rate of change of cost with respect to the number of units produced. Which is X. So a derivative of whatever our original function is always the rate of change of that thing with respect to the variable. So in this case, X is the number of units that we are producing. So the marginal cost tells us the change in cost with respect to the number of units produced, which we could say in another way, and this would be the approximate change in cost of producing one more unit. So we're going to see how these two are related in a little bit in an example. So if we are producing 300 water bottles, we have a certain amount of cost. So marginal cost would tell us how much is our cost going to increase if we produce one more water bottle. And so it's not necessarily always going to be the same. It'll depend on our cost function. It might cost more at the beginning if we are not producing very many things. Each one might cost more to produce. Whereas if we are producing more, there might be a more efficient system, so each one is costing less. But we don't necessarily know. We don't know until we have the function. So let's look at an example of this. No, my mouse isn't working. There we go. So here is our first problem. So I'll give you a moment to read that and take it in. Okay, so this company, so a company manufactures automatic transmissions for cars. The total weekly cost of producing X transmissions is given by this function. So we have our cost function, and our first task is to find the marginal cost function. In section 2.7, we get to use the power rule and the other rules of derivatives that we have learned. So we do not have to go through the limit definition of derivatives. We can go straight to finding C prime using the power rule. So this is a little review of what we were doing on Tuesday. So take a minute to work out what this is going to be. All right, so what is our marginal cost function here?
Um, 600 minus 1.5x.
Yes, exactly.
Can we switch those?
Yes, you
Okay.
can, as long as the,
Negative signs out front.
yeah, exactly. You read my mind. So this would be the way if we're just going term by term to take the derivative, that 50,000 goes away completely. That's our constant. So something that doesn't have a variable in it is just 0. The 600x just becomes 600 when we do the derivative. The x lowers by 1. And then for that last term, the 2 is going to multiply with the 0.75 to make 1.5, and the x gets its power lowered. So this is the marginal cost function, but if you want to switch these, that is fine. So on something like this, we actually don't have any work to show, because the power rule is so straightforward. So this function is going to tell us when we change the number of units we're producing, we'll see how much the cost is changing. So let's look at part B. So if we want to know the marginal cost at a production level of 200 transmissions per week, what are we going to do to find that?
Plug 200 in for X.
Yes, exactly. So we have our marginal cost function. There it is. I keep losing my little pen on the screen. Oops. So we are plugging 200 in for X. So now we'll have C prime of 200. And we'll just evaluate.
Now, for something as easy as that, do you want us to show our steps, or would you prefer our steps shown, or could we just write 300?
I would like to see this step. So I know that you know where the 300 came from. But if you do 600 minus 1.5 times 200 all in one step, that's fine.
Is the 300 in dollars?
That was my next question. What is our units here? Not quite just dollars, but dollars is part of it.
Yeah, I would think
Dollars
it's
per
dollars as
transmission.
well. Dollars per transmission, yeah. Sounds right.
Per transmission, yes, exactly. So we have a rate of change. So this would be $300 per transmission. Ooh. And it would be fine also, since transmission is kind of a long word, to say dollars per unit. And it might also be more normal to write $300 per unit this way. Any of these would be fine. But so we do have a rate of change. So that means that if we are increasing our production from 200, the cost will be increasing at a rate of $300 per transmission. So all of this stuff, we have our things we are doing on Tuesday to take the derivative to find the marginal cost function. Otherwise, we're just evaluating using that marginal cost function. So next question, I've already sort of said this out loud, but okay. Little side note before we actually do part C, on some of the homework problems, there is like a last part that says interpret this in words or explain what this means in words, and those are not optional. Sometimes I notice that on homeworks that people are just skipping those, and if that's the one that I graded, then you're going to lose points for those. I'm more lenient on the actual answer for those because I know interpreting it in words is something that takes practice, but if you're not answering it at all, then you're going to lose that point. So be careful of that. There will also be an interpret in words question on the test. Okay, so what does part B mean in words? Our answer for part B.
The cost of manufacturing 200 transmissions is $300 per unit, per transmission.
Not quite, and that is a really common thing to think at first with these marginal costs.
Any transmission above the 200th transmission would cost $300 to make.
Right, exactly. So those first 200 transmissions, we don't, at this point, we haven't done any work to figure out how much each of those cost. We're looking at how much it would cost to make more transmissions above the 200. So at a production level of, oops. Let me make this bigger so it's legible. So there's a handful of ways to say this, and so there's not always one right way, but at a production level of 200 transmissions, the cost is increasing. At a rate of $300 per unit. And so we also have to be sort of careful with our understanding of this as well. So if we're making 200 transmissions and then we add like 100 more after that, that's too much of a change for us to use marginal cost. So marginal cost is the derivative, which means it's talking about that instantaneous rate of change. So that's why, and we'll see this in a little bit again, up here, oh, and it was on the previous page, let me go back. I said the marginal cost is the approximate change in cost of producing one more unit. So it's really that rate of change right around 200. Whereas if we start making more and more and more, the marginal cost is going to keep changing. So the marginal cost is a function just like cost is. So marginal cost is changing depending on the number of units as well. So we have one more question so we can sort of compare this idea of instantaneous rate of change and sort of our average rate of change that we were using last week. So D, we're gonna ignore marginal cost for a second. We want to know the exact cost of producing the 200 first transmission. In order to find this, I'm going to write our cost function again, so it's handy.
Is this just a plug and solve?
Yes. What are we going to plug in?
The 201. Yeah.
So if we plug in 201, that is part of what we need to do. So we'll just go ahead and do that. Oops. Which this is the type of thing that you can just plug all of this straight into a calculator carefully.
Yes.
You can always do it in steps if you would prefer. So for this C of 201, I got 140,299.25. Did anyone get something else?
Almost done.
I got the same answer you did.
Okay, awesome.
Yeah, same.
Great. So that's probably right. So this isn't quite the answer that we're looking for though. What is this C of 201 actually telling us?
The total cost for 201 transmission.
Exactly. So that's
So divide that by 201.
not quite, because we know from our marginal cost that not every transmission is costing the same amount to make. The
Hmm.
first one might cost different than the 21st one.
You have to subtract the cost of 200 from that.
Exactly, yes. So if we know the cost of 200 transmissions, then we can subtract that from the cost of 201 transmissions, and that'll give us the exact cost of that last one. So we'll go back through all of this. And we get 140,000.
So 299.25.
Yes, exactly. So what we're looking for here is the total cost of making 200 transmissions, or excuse me, 201 transmissions minus the total cost of making 200 transmissions. And we do get 299.25. That one is just in dollars because this isn't actually a rate. We were just looking for the cost of that one single transmission, that 201st transmission. So let's compare what we're seeing here. So for part D, I think this was D, we found that that 201st transmission was 299.25. In part B, we said that at a production level of 200, the rate of change is $300 per transmission. So these numbers are very close. They're 75 cents off in this case. But this is why at the beginning I mentioned that this is the approximate change in cost of producing one more unit. The exact cost of producing that 101st transmission is that 299.25. But we can see it's a lot of work to go through all of that just to find the cost of that one transmission, where our marginal cost function gives us this nice little function that can tell us the change in cost for any production level. So it's sufficiently accurate that this marginal cost function gives us a much more convenient and efficient tool to find the increase in cost for each additional unit than going through all of this for any time we want to figure it out.
If it's the change in cost, does that mean that it's $299 more than it was before? Or does that mean that it's $299 to produce it, so the change is only 75 cents?
It means, so it costs this amount, the C of 201, that was the total cost that it takes the company to produce 201 transmissions. And the 140,000 is the total cost it takes the company to produce 200 transmissions. From 140,000 to 299.25.
I see. Okay, cool. I see.
And
So based on that calculation, then each transmission that was within the 200 was $700 a piece. You take the 140 divided by 200.
So the cost is changing though. The cost for each transmission is changing.
Okay.
So if we did the same analysis for the cost of the 100 first transmission, it's going to be a different value. And so each transmission is going to be changing. The cost of each additional transmission is changing. And so I'm going to bring up a Desmos real quick, just so we can look at a graph of what we're seeing, and then I'm going to draw another graph to try to visualize this. Here we go. So we have whoops, what's happening? There we go. C of X was 50,000 plus 600X minus 0.75X squared. So I need to change that. My mouse is really not working very well today. So on Desmos, we can go up to this little wrench and change. So we are looking, we don't need anything below 0 because we're talking about transmissions. And I'm going to put this on about 300 so we can see the transmissions we're working with. Y is our cost, so cost will not be below $0. And we just saw our costs when we were plugging in 200, 201 was over 140,000. So I'm going to just put in 200,000 just to see. So this red line, red curve, is our cost function. So if we're not producing any transmissions, we still have $50,000 in costs. So those are probably overhead costs and like initial equipment and things like that. But as we increase the number of transitions we're making, each transmission is costing a little bit more, but it's not consistent. So this is not a straight line. The curve is fairly slight here, but it's still not going up at a consistent rate. So these first few transmissions are more expensive than when we get up higher. And we can see on this graph if we're producing 200 transmissions, that's our $140,000. And if we go up to one more, I wonder if, yeah, there we go. We have 299.25.
Well, just a thought, because I used to work for a dealership, and when they do transmissions, it is extremely expensive. And typically it's more expensive to get a transmission done at a dealership than like a mom and pop place. But I would assume
this one because I work for O'Reilly Auto Parts. So what happens is that the dealership eventually buys it either aftermarket, either from their internal supply person or from, say, O'Reilly's or AutoZone or Napa. And from there, they have a certain cost. And from the dealership, they have to mark up that price. They have to upmarket. So it's like an upmarket, like a 300% on the transmission from the cost that they get it. So then they upmarket for their customer, and their customer, that's how a dealership makes money, is because they have to upmark everything.
That makes sense. I mean,
Yeah, and thank you for that. Those are pieces of knowledge that I don't have, so I appreciate that input. And we are going to be focusing, like all of our problems will have our function given to us. So there's never going to be a time when you have to find the cost function based on all of those things you're talking about, because there's a lot that goes into it. So we'll be working with, we'll have our cost function, and that'll be the one we are going to go with. So how accurate these are from the book, I can't comment on. So, thumbs up. Oh yeah, okay, so our, so this is our cost curve. And so we know that a derivative, so if we're just thinking of this as a regular function and thinking about its derivative, we know the derivative gives us the slope at the tangent line at that point. So when we look at marginal cost of 200 transmissions, we're going to be looking specifically at the slope of the tangent line that would hit the curve right at this cost, which is the instantaneous rate of change. So I am going to draw a picture of what I am talking about. Let's see. So this is not going to be, oops, totally accurate, but if we were zoomed super close in on that cost function, and I'm sort of exaggerating it here, and let's say this is sort of, we're gonna start 200 here and 201 here, just for the sake of being zoomed in. So our C prime of 200, our marginal cost function, is telling us the slope of this tangent line. So C, oops, it's not a C, C prime of 200 is the slope of this line. Because that's the tangent line that's touching right at 200. When we found the change in cost from 200 transmissions to 201 transmissions in this exact way, we were actually finding the change from the point on the graph at 200 to the point on the graph at 201. So in that case, we're actually finding the slope of this line. So if we're super zoomed in, this looks like a bigger difference than it really is. But that's why the marginal cost really is just giving us an approximation, because the tangent line has a little bit different slope than the line that's actually going from 200 to 201. Since we can't talk about the cost it takes to make like an extra half transmission or an extra quarter transmission or something like that. So here, or actually it's this change in Y from the 140,000 to 140,299. That is the 299.25. We are always going to be using the marginal cost function in this class. Pretty much, there might be a couple of homework problems where you need to find the exact change to compare them. But after this initial introduction to marginal analysis, you won't have to worry about this exact cost and the difference. We're just going to be using that. So we're going to build on this. This is sort of our introduction to this marginal stuff using marginal cost, but we're going to build on this and talk about revenue and profit as well. Any questions at this point, or anything that's bothering you about these things?
I got to say, this is pretty interesting stuff.
It is, yeah, I agree.
I like the illustration on the graph that you made of the difference between like the slope. I really did like the illustration. I think that helped. It really did.
I'm glad.
Mine is way worse, but I'm going to be using yours if you have the notes. So thank you.
Oh, yeah, it's hard to make good graphs on my little tablet. There's also a better graph of this in the book as well, if you want to see a nicer
What page is
drawing,
that
but,
on? I will definitely check that out. Is it 157?
164.
164. Okay, awesome.
I'll put that in the notes here too, just as a reference. Okay. All right, so this is a different example. It's also, this is directly from page 172 of the book, problem 46. So you're welcome to write this down in your notes or just look in the book. So I'll give you a moment to do either of those things. Okay, so sorry, I thought I was going to cough for a second. Okay, so the price demand equation and the cost function for the production of HD TVs are given respectively by these two equations. So a price demand equation means that we can sell X number of units at a price of P. So if you have taken any business or economics classes, you would talk about like supply and demand and price demand as well, depending on the class. So our price demand equation is this equation, which tells us that if we are charging P dollars for a TV, we will be able to sell X of those TVs. And so we also have the cost function, and that is the same kind of cost function that we saw in the previous example. So our first question, and this problem is going to have multiple parts we're going to work through. I think there are I parts to this problem, and so we're going to be working with these equations for a while. So our first part, part A, is to express price P as a function of the demand X and find the domain of this function. So we're going to hold off on the domain for just a moment and look at, we want to express P as a function of X. So this is our price demand equation. This phrase, express P as a function of X. What does that mean? What is that asking us to do?
So you rearrange the function so that P is on one side and everything else is on the other?
Exactly, yes. So we're gonna get this function so that p is by itself. So however you do that is up to you. I'm just gonna swap the 30p and the x. So we have 9,000 minus x on one side, adding 30p to both sides and subtracting x from both sides. And then we just need to divide by 30 everywhere. So do be careful here. We don't want to round when we're working with our functions. So if you do 1 divided by 30, you would get 0.03333. And so in order to write that as a decimal, we would be rounding, which we don't want to do. Once we get an answer, we can round for like the cost of something or whatever. But when we're working in our actual function, we want to leave fractions in their unreduced form. Or sorry, in their reduced form. Okay. So expressing price p as a function of x just means that now p equals something with x in it. So this is basically now saying that if we want to sell x units, we should charge the price p. So x and p still have the same relationship, but it's just written in a different way. So our next question is to find the domain of this function.
I'm sorry, just real quick. That's 1 over 30x, right? Not 1. Well, I guess it doesn't matter. Never mind. I'm sorry.
No, it's fine. And I think I see where that's being confusing. Yeah, 1 over 30x on the side.
There you go.
or it could be x over 30. Yeah, my x was a little lower than it should have been. Okay, so that is our price function in terms of x. So now we want to know the domain of this function. So the domain is all of the x values that we could put in here. So if this were just a regular function and we did not have any context, there would be no problem with any x in here at all because there's no x in a denominator and there's no negatives in a square root or anything like that. However, when we are working in a word problem like this, we have to think of the actual context. So what is the smallest thing that x can be?
0.
0, exactly. X can't possibly be less than 0. So smallest x, I'm just going to write this in words for now. So if we are selling x units of a thing, it's impossible to sell negative things. So our smallest x is 0. So we also need to figure out the largest x. And so we have to sort of think, if you feel really good about graphs of lines and what this looks like, we could think about that. But we can also just think, at what price would we sell the most TVs?
Would it be 30?
Not 30.
300.
Are you saying 300 for X?
Oh, one piece 300.
Or, oh, not quite. So that would be the price when X is 0. I'm seeing in
Jason
the
said
chat
9,000.
9,000. So that is the largest X we can have. That is true. And that is when P is 0. When P is 0, X equals 9,000. And
I
we can
assume
find
that's
that by
30 times 300. Oh, it goes
That
back to the
is-
original equation.
Yeah, if we look at the original, if we put 0 in for P, we would get 9,000.
Gotcha. Okay.
And so one way to think of this too, I'm going to move this away for a moment. If we think of it on the graph, actually, let me. So X has to be between 0 and 9,000. Wow. So if we think
So
of
if we were
this-
to explain in words what happens at 9,000, why is that a limit?
Because, so let me draw the graph and then I'll explain in words because I think it's easier to visualize. So if we were just to graph this line, P equals 300 minus 1 over 30x. So that is in the form y equals mx plus b, it just has mx and b switched. So the y-intercept is 300. And then it has a slope of -1 over 30. So it'd be going down, and all we really care about at the moment is that the slope is negative. So what we're seeing here is that this is the function P equals 9,000 minus 1 over 30x, where x is on the regular x-axis and P is on the y-axis. So we do not want any x values that are going off in this direction because that would be a negative x, and that doesn't make sense to sell negative products. We also don't want any part of the graph that goes off in this direction because then we would have a negative price for our TVs, which also doesn't make sense. So we have to be working only in quadrant 1 where both x and p are not negative. So really what we're looking for is that we know x has to start at 0. And then this is the x-intercept. Which is where p equals 0. So that is what this means graphically. We want neither of our things to be negative, so we have to look at just the x values that are keeping us in quadrant 1, which means starting at 0 and going right up to where x would cross the x-axis. Another way to think of it is if we are thinking about price demand in this, and I'm sure there are various experiences in price demand equations in this class, but the basic principle, and things are more complicated than this, but basically, if we increase the price, fewer people are going to buy it. So and the other way around, if we decrease the price, more people are going to buy it. So the very smallest x is going to be 0. That's the fewest things we can sell. This is the smallest it can be. So our domain of a price demand equation will always come from x being 0 and p being 0. Because those are the two extreme situations that we could see.
Is that always the case when you're talking money? Or can that vary?
If we are looking at a price demand equation specifically, that will always be the case.
Okay.
So would it be, would the concept be that that only 9,000 units are demanded? Like the demand doesn't go beyond 9,000?
Right, yes. Exactly.
Like if there's only 9,000 people in the world and all 9,000 TVs get purchased, there's no other person to demand an extra TV.
Right, yes.
So if we have a different function where we can't like easily see that x-intercept, how do you want us to find that?
That won't happen.
Okay.
But the
Nice.
the way would be to just plug in p and find, or p equals 0, excuse me, and find what the x-intercept would be. And if it wasn't a nice number like 9,000, it would just be whatever it happened to be.
Okay, thank you.
We will have some more complex price demand equations in the future, but you won't have to find the domain of those. And these, again, these are the kinds of things that analysts and economists are making, these price demand equations. So we're just going to take the price demand equation at its word and then use it to do our calculus things. Okay, so we have, let's see what we were doing here. So we wanted to know the price as a function of x, and the reason we're doing that will become clear in a little bit. And we found its domain. So these are the constraints of x we're working with. So this company could make 0 TVs, and it could make up to 9,000 TVs, but it's never going to make more than 9,000 TVs. So our next question is to find the marginal cost function and use proper notation. So our cost, I'm going to go up here. So what is our marginal cost here?
$30.
30, exactly. So that 150,000 is the constant, so it goes away. And now we have just 30 in front of our x. So this is a situation where it actually does cost the same amount to make every additional TV, because this function doesn't have an x in it. So it's going to cost $30 per TV, no matter how many TVs we've produced. So this can happen, that the marginal cost is the same for any number of TVs. I want to highlight this part of the question, use proper notation. It would not be correct to just write 30. It is correct to write c prime of x equals 30. So this is a function, and we were asked to find the marginal cost function. This is not a function, it's just a number. So just having a 30 sitting there doesn't give us any context or information about what it is. So the c prime of X equals 30 should be the whole answer to this question. Okay, so we're going to build on this example in just a moment. We're just going to pause to talk about the next important thing in section 2.7, and that is revenue.
Are we coming back to complete 46?
Yes, we're going to be adding on parts to it as we go through new things. So yes, we will be coming back to it.
Okay.
So what is revenue in
Real quick, is this
words?
part of B still, or are we moving on to C?
Oh, it is not part of B. We are going to get to C in just a moment. So this is a little interlude before we get to C. It's not part of B though.
Revenue is the amount of money coming in before expenses.
Yes, exactly. So this before expenses part is key. So our cost function, we have cost functions, and that's what takes care of expenses. Revenue is just the money coming in. So our cost function is going to have nothing to do with the revenue function at this time. And we can always find revenue. And so we're assuming at this time that our company is selling just one thing. So our X is some product that we're selling. So if we are selling X units at P dollars each, what would our revenue be?
Whatever P is.
So
it'd be X times P, right?
yes, exactly. So our P is the price of each item that we're selling. And we're selling X of those units, X of those things. So our revenue is going to be X times P. So if I have a little coffee stand and I am charging $2 for coffee, that's the P. I'm charging $2 per coffee. If I sell 5 coffees, that's my X. So if I'm selling 5 coffees at $2 each, I would multiply those to get $10 for my revenue. Notice, this is a little foreshadowing, and we're going to come back to this in a moment, but notice that R is supposed to be a function of X, and we have an X and a P in here, which we're going to leave for a moment, but just take note of that. So marginal revenue, R prime of X. So marginal is always going to mean the derivative for all of this stuff. Marginal whatever means take the derivative of whatever we're looking at. So in words, what would be the marginal revenue?
The rate of change of revenue at a given unit sold.
Yeah, that sounds good. So the rate of change of revenue at a given units sold, which is our X. So this again is not necessarily consistent. The increase or decrease, the change in revenue, if we sell a few more units at the very early stages when we're not selling very much, might be different from the amount of revenue or the change in revenue when we're selling a lot of units. So marginal revenue, again, depends on how many units we're selling at that time. And just a note, the X, if we are working in one context, which we will be, we're going to add to that number 46 in a little bit. The X is the same X, even though its meaning is a little bit different in different contexts. So in terms of revenue, X is the units that we're actually selling. In terms of cost, X is the number of units we're producing. And so we're going to assume that that X is the same. We're going to sell all of the units that we're producing. Okay, so now that we have these two pieces of information, these two new words, we will be continuing the example. So same example as before. And we want to find the revenue function. And state its domain. So these parts are building on each other. Not necessarily every part will be necessary for the next questions, but we do need to use some work we've already done in order to answer this question. So think about it on your own for a little bit, and then we will put it together. So a key part of this question is the X. Revenue should be a function of X, which means X is the only variable in this function.
So then we will use the equation 300 minus 1 over 30x.
We will use that. So how are we going to use that? Let's put this together.
Mathematically.
Yes. That's a pretty safe answer in this class. So let me make this page bigger so we can fit a little bit more onto it.
If the equation for Rx is x times p, wouldn't you just plug that in for p and then like distribute x?
Exactly, yes, that is what we're doing.
So smart,
Yep.
Matt.
Yep. So if our revenue is always X times P, units we're selling times the price per unit, that's why we wanted P as a function of X in part A. So now we have X, which is the number of units we're selling, times P